I'm Chris Mutlow. I'm the director of Rail Space, and I'm also the senior person responsible for NSTF. We're very pleased to welcome you today because NSTF's been a long time in the coming, and it is really built specifically for you guys in industry to make use of. The whole idea of the National Satellite Test Facility came out of a study that was done quite a number of years ago now, called a Facilities Gap Study, which was to identify what was needed in the UK to support the space industry and what was needed in terms of test facilities to make sure that the UK could stay at the forefront of delivering space hardware around the world. Obviously, there are a number of test facilities already in the UK, but one of the things the Facilities Gap Study identified was that we needed to have them all in one place to avoid having to keep packing things up and moving them around the country, and that we needed them of sufficient scale that we could support all of the different activities that the UK was trying to achieve, both in the civil programme and also in the military programme. And this has meant that we built a facility that is somewhat larger than we had originally envisaged. During that time, we've tried to stay very close to all of you guys in industry and make sure that what we've done is matching your need. So we started out with a particular design, which we got the money for. I think this was probably back in about 2017. And very quickly, we discovered once we started to talk to you about the workflow that you were going to put through the building, that we needed to rethink that. So we've tried to kind of rejig the design of the facility to meet your needs as we've gone along, and made sure that we've tried to tailor it to those needs. Some of the needs for the MOD side of the house have grown, and so the scale of the facility has grown. So what we have now is a pretty comprehensive set of test facilities. We've taken some new directions in some areas, in that we're not building a very large acoustic chamber. We're relying on a more modern method, the DFAT method, which we'll hear about later, which requires something more like Led Zeppelin's PA stacks than the 1,000-ton concrete bunker that has traditionally been used. And also in some of the areas of mass properties, we're trying some new methods there that will, we hope, speed up the testing of spacecraft. So the building has been a long time coming. Obviously, we'd hoped to have it sooner than that. The initial delays were due to various changes in government and the decision to move the original bid from the standard grant rounds to the Industrial Strategy Challenge Fund. And then I think we had a general election which delayed it a bit further. Anyway, we're now where we are. We kicked off quite a while ago now, and I'm sure Sean will take us through that. Progress has been good during the COVID period. I have to say our builders, Mace, have been excellent at keeping things on track. Not all of our suppliers have been able to do as well as that. And we have had a few difficulties, which I'm sure will be discussed later. But what we have now, I think, is a very fine building, and what the test equipment that is going in there, I think, is state of the art, and we should be very proud of what we have. So without more ado, let me pass on to Chris Costelli from the Space Agency, who will talk to you a bit more about it. He is the chair of our oversight board, and he has been working closely with me right from the beginning of this process, together with colleagues from Innovate, to make sure that this happened. So Chris, over to you.
Thank you for that introduction. And it's great to be here on this webinar as we approach the end of the construction phase of the National Satellite Test Facility. It's already been an exciting start to 2020. Just before New Year, on Christmas Day, we had the launch of the Webb Space Telescope, the next great observatory, with the UK-built mid-infrared camera on board, which was actually assembled and tested by the team of engineers at RAL. And as we see the Webb being commissioned, its mirrors unfolding and the instruments being switched on in deep space, it reminds me of how complex and increasingly sophisticated space missions have become since I've certainly been involved in the space program. And in turn, this points to the need for more capable and cutting-edge space test facilities. So, the completion of the NSTF then will make this facility the first of its kind in the UK, and will help us get larger and more capable and more complex spacecraft ready for launch, thereby meet the needs, the future needs of the sector as we develop and invest in national missions. It's also the key building block in the UK having, for the first time, an end-to-end capability to design, build, test, and launch our own satellites as we look to the exciting first commercial launch from UK soil later this year, fingers crossed. In a moment, we'll hear about the capabilities of the facility and some of the exciting opportunities it will open up for the sector. But, getting to this point has been the outcome of a lot of collaborative effort going back to 2016, where work was done to identify key strategic gaps in the UK space infrastructure. Back then, that is STFC, RAL, UKSA, worked together to develop the business case to secure something like the 100 million or so investment needed out of the first call of what was called the Industrial Strategy Challenge Fund to build this facility. And following approval, construction started sometime in the summer of 2017. As you already heard, since then I've been chairing the steering board that has overseen the development of the facility, along with engagement with ESA, who have obviously vast experience in spacecraft testing, and importantly, the user community, who will have access and of course use the facility, making sure that when it's ready, it's fit for purpose. I just want to, re-emphasize, NSTF wasn't someone's pet idea. As Chris Mutlow has said, the idea of a capable assembly and integration test facility goes back to work done through the UK Facilities Gap Study or Survey in 2016. This was commissioned by the UK Space Agency as a comprehensive assessment of the existing facilities available in the UK for the development and test of space hardware. And as the name suggests, set out to identify any capability gaps constraining our sector from achieving the growth objectives laid out in the sector action plan. This plan, for those who were not around at the time, was a 20-year strategic forward look for the UK space sector, developed by a large sector-wide team of industry and academic space experts, published in 2010 as the so-called Space Innovation and Growth Strategy. And this coordinated working between the sector and government has been a real success. Since it was published, we've seen rapid growth with almost a doubling of turnover from 8 billion in 2010 to around 16 billion today. So to continue this growth, an NSTF type facility emerged as a clear top priority, as the UK lacked, as we've heard, compared to many other leading space nations, a one-stop shop for spacecraft level environment testing, and importantly negates the need for system integrators, spacecraft builders, if you like, to transport spacecraft and teams to mainland Europe for extended testing. So in addition, there was also a compelling case to establish a national AIV hub on the Harwell campus due to the attraction of SMEs and large space companies, both national and international, at Harwell, and the growth of the space cluster. So just to summarize then, I think it's fair to say that the NSTF really is a visible commitment of government to space. And by working collectively with the engineers at RAL, the Research Council, STFC, who have all the expertise in developing and running complex science facilities, our sponsor department, BAYS, and the sector, it really highlights the team nature of space and the value government investment and strategic thinking can bring to the UK's future. As it says in the recently published National Space Strategy, the gears of government are here to unleash innovation in the space sector by catalysing investment, delivering space capabilities and missions, and importantly, championing space. Thank you.
Afternoon, everyone. My name is Sean Stewart. I'm the NSTF Program Manager, responsible for delivering the whole facility to RAL Space on behalf of the UK space industry. As we've heard from both Chris's just ahead of me there, the building is being built in response to the UK Space Agency's facility gap study or analysis, which was commissioned in 2016 and published in 2017. What I'm going to do now is just walk you through the build process, how we've come to where we've got to, and show you what the NSTF looks like. Matt and his team will follow me and they will tell you how the building is going to work. So the NSTF has been designed from the ground up to meet the requirements of the space industry, and it comprises of the following sort of major blocks. We have a domestic wing where we'll have the offices, the meeting rooms, the toilets, the lifts, the stairs, all the things that you're going to need in order as a customer to come into the building and do what you have to do. But that's kind of basic. The really exciting stuff is the test facilities. So we have our airlock. This is where a satellite will start and end its journey through the NSTF. It'll be delivered into the airlock before coming into the main facilities, and will go back out through the airlock at the end of a successful test campaign. The facilities, as we go around the building, we have our thermal vacuum chamber, we have its plant room, and at the top end of the building there, you can just see the 3 storage cylinders, for the 2 for liquid nitrogen and 1 for gaseous nitrogen, which will regulate the TVAC chamber. We have 2 clean rooms in the building, and these will be the home bases where the satellite and a customer will base themselves for the duration of the time that they're in the NSTF. We have our vibration facility and the acoustic hall, and Chris mentioned those a little while ago in his introduction, doing things slightly differently, certainly on the acoustic front, but we have a horizontal and a vertical shaker in here, and people will talk you through those in a little bit more detail later on. The EMC chamber, from a construction perspective, is by far the most complicated part of the building, and unfortunately it's the piece that has tripped us up recently, but we're working through the problems we have there, and you'll see later our handover timeline. And then we have clean room 1, which is the second customer base, and a main corridor up and down which satellites will travel when going to and from the 2 customer clean rooms to the various test facilities. You'll notice that there are different shades of green on this particular slide, and they denote the ISO classification of the rooms. Clean room 1 is at ISO class 6, so that we can have optical instruments being worked on in that space. The rest of the facility will be at ISO class 8, and the airlock can fluctuate between ISO class 9 and ISO class 8, depending on whether the outside door is open or closed. A quick canter through the construction project in pictures then is where I thought we'd go next. We said that the study was released or written in 2016 and published in 2017. It took right the way through to about the summer of 2019 before we actually got the funding, so we couldn't start any works. But in October 2019, we took over this brownfield site. This photograph is taken after we'd got rid of some trees and some shrubs. The next job we had to do was move that fence and move it to the other side of our compound, because the buildings in the far distance there belong to the nuclear license site, and we had to maintain their security. And by the end of October, we'd actually started scooping the earth out of this particular piece of land. By Christmas of 2019, we'd dug an Olympic swimming pool sized hole into which we had dropped the basement for the seismic blocks that have gone into the vibration facility. You'll notice that the basement is circular, not a traditional build by any stretch of the imagination, and we managed to knock about 6 months off our build program by buying sections of tunnel from the Crossrail project, flipping them through 90 degrees and dropping them down into the ground vertically. So that was an innovative bit of building work that we did. We also dug another Olympic-sized swimming pool hole at the other end of the building, underneath which is our clean earth mat and the rainwater attenuation tanks for the building. By spring of the following year, as you'll see, the concrete base has been, the floors have been poured, the foundations are in position, and we've started to build the steel frame around the 2/3 of the building as it stands at that stage of the project. But that's when COVID hit us, and that brought obviously restrictions on travel, reduced numbers on site, social distancing, and daily lateral flow testing was enforced on everyone who was coming onto the site. We've all endured lockdown, but it has caused the project a number of fairly severe problems. But we had one silver lining because of COVID. It meant that we could get our thermal vacuum vessel from Portsmouth all the way up to Harwell with relative ease because the roads were broadly closed on the day that we were allowed to do it. By the time we got to the summer of 2020, you'll see that the TVAC has been put into position in the building. The framework is almost complete, and if you look through the building, you can see there are some patches of dark on the far walls, and that's because we're already starting to hang the walls of the building. So we're making good progress by the summer of 2020, and by Christmas of the same year, it's all starting to look pretty complete, at least on the outside. When we drop onto the inside of the building, we've got bare, dusty concrete floors, dusty plasterboard lined walls, and absolutely no ceilings. So you certainly wouldn't want to bring a satellite into this building at the moment. Jogging through 2021, by March, we'd started to tidy things up a little bit. By June, we'd managed to get the resin floor down, and in this picture, it's been protected by a series of mats. Some of the walls are starting to go in, and we're just starting on the ceiling. By September time, the resin floor is down and complete, the ceiling is almost complete, and all of the clean room walls are now in position. And by December, so this is just before Christmas of last year, it's starting to look like a facility where you might actually consider bringing a satellite for testing. As we look down the building, we're looking towards the airlock in this picture. You can see a couple of dark shadows in the far distance. Those are shrouds for the thermal vacuum chamber. We're in the process of getting ready to install those in the next couple of months. And you can see the big 10-meter tall door, one of the big 10-meter tall doors going into the EMC chamber. In terms of what we can actually do now and our short-term plan to get Matt and his team into the building, the team currently has access to the TVAC plant room, the TVAC clean room, and clean room number 2, and that's where we're doing all the prep work for the shrouds that are going into the TVAC chamber. In February, Matt and his team will move into clean room 1 and start their characterization of the building and some of the equipment that we have already bought. In May time, when our specialist installation engineers have completed their work, we will be moving into the vibration facility. And then, all things being equal, in November, we will finish in the EMC chamber, and by December, the whole building will be handed over to us. So that's broadly the end of my slides. What I thought I'd do now is just show a quick start to finish from bare site through to where we are today video. So thank you, everyone. That's the end of my slides. I look forward to answering your questions later on in the presentation. But for now, I'll hand over to Matt, and apologies for my ineptitude at the start there.
So welcome to this part of the webinar. My name is Matt Fletcher. I'm the Environmental Test Division Head here at RAL Space. And I'd just like to take the opportunity to thank Sean and his team for all the progress so far in what's shaping up to be an excellent facility, and congratulate them for working through what has been 2 years of pandemic and not an easy condition for a project to build within. But a facility is not just made up of equipment, but the people and processes are just as important. And I hope that we're going to be able to give you a flavour of all of this today. I'm going to give a very brief summary of NSTF operations, and then the following group leaders will expand in more detail on their various areas of responsibilities. So as a as a facility overview, the headline for the facility is NSTF has been scaled and sized, capable of testing satellites up to circa 7 tons. For thermal vacuum, vibration, acoustic, electromagnetic compatibility, antenna measurement, mass property testing, all within clean conditions. It's operated as part of the Environmental Test Division. That's my division here in RAL Space, with significant heritage in the environmental testing of satellites and subsystems. For people who are not familiar with our site, we're located in the UK, 16 miles south of Oxford, next to our existing test facilities, many of which have been operational for decades. So what you'll be able to see on the left is an aerial view of the Harwell site, not the entirety of it, but most of it. And what's circled is the NSTF, as was about a month ago. The NSTF is operated by the same team who are and will continue to operate the existing facilities. And the image that's just appeared describes the range of just our thermal vacuum test chambers, which we currently have under our operation. The largest of those chambers, the one right on the right, is the one as part of the NSTF. Although the smaller test facilities are not part of NSTF, they are regularly used and accessible to users outside of RAL Space. We have clean room provision, ISO 5, 6, thermal chambers, vibration, pyroshock. There are real main capabilities, but the talks today are very much focused around NSTF. So in terms of the timeline, and you can see the people at the bottom very interested when we took this photo in this timeline. The project, as Sean has said, basically completes in December, and there's a growing completion as we get to there. And there's a growing takeover. So there's a managed handover between the build team and the operational team, which continues this year. And we'll be taking it all the way to 2023, and some more details are coming. So the following bars basically articulate where the build team are responsible for the equipment, and the manufacturers will be completing their site acceptance test. So the EMC and antenna measurement system will be completing this year. The vibration earlier, TVAC a little later. Mechanical ground support equipment, that's the loading trolley for the TVAC, is probably one of the first pieces of equipment that will come to us. And then the mass properties machines. Once those have completed their site acceptance tests, my team will be then characterizing them, not just the technical equipment, but also the building itself. The building itself is a very complicated thing, and it's required to be operationally robust. So all of these bars you can see summarize into the summer of 2023 is when we should be ready for users to come and use the facility. During the characterization period, it's not a simple activity. Our overarching goals are to make sure that it is safe and appropriate for use, the performance is characterized, the standards for quality assurance that we're putting in place is supported, and we can train and prove competence of the operational team. It's not simple. We will be conducting fault cases, will be tested, recovery modes will be exercised, equipment is going to be tested to the limits to ensure all the characteristics are understood, captured, and confidence in the equipment is gained, and of course documented for the future. We are going to be supported in that testing, not just from the use of test masses, etc., but for use of representative items. As a test centre, quality is a foundation for our operations, and we are going to be using this time to prove to ourselves and the relevant auditing bodies and customer bases that we conform to the required standards. Isabel Martinez will expand further on the quality aspects. However, the headline is that we're aiming for the ECSS QST 2007C, which is the ESA standard for test centres, which is going to be underpinned by our existing EN 9100 certification we have in Environmental Test Division and the wider and broader ISO 9001 standard that exists in RAL Space. And all of this is going to ensure that it works as intended, it's ready for customers to with space hardware. But as I said before, people are one of the foundations we rely on. And what you can see that's just appeared is a slightly difficult to read organogram, which shows the current people we have in the Environmental Test Division who are operating or preparing to operate the test facilities. The boxes marked in blue are people we have, all permanent employees, and in orange, the posts we hope to fill over the coming year or so. And to the right does not describe a crack in the building, it describes our staffing increases. To the left of the dotted line, which is today's date, shows the reality of who we've hired and how many we've hired, and what's to the right is the ones we intend to hire. And as you can see, that matches with our operational needs in terms of readiness. You're going to see during the following presentations some more details about the teams. But as a headline, collectively, there's over 200 years of testing experience within the existing staff. And as we hire more staff and experience grows, that's only going to increase. So to access the facilities, the NSTF is operated by the Environmental Test Division of RAL Space, which is part of STFC and UKRI. And access to the facilities will always be through a commercial contract. UKRI is the legal entity customers will contract with. However, all the engagements will come through RAL Space. If you have interest in using their facilities or exploring their capability, then our preferred contact is through our business development team, lead on the facilities. That's Dr. Sarah Nash. We really are delighted to hear about future work and will happily engage with projects, giving information about capabilities, and when the time is right, we're happy to give a proposal to your specifications. But of course, the facility may not immediately match everything you need. RAL Space has got significant heritage in designing and building space hardware and associated ground support equipment. In fact, we're effectively building the NSTF. So if the current facilities don't match your needs, we do have the ability to engineer modifications, provide interface equipment specific to your requirements. So don't forget to talk to us about that as well. So the next hour or so is going to be led by the various group leaders who will give you a more detailed insight into various areas. And at the end of all the presentations, there'll be an opportunity to ask questions. So either store up your questions for this or type them into the Q&A now and we'll pick them up at the time. At this point, I would like to hand over to Isabel Martinez, the QA and SHE group leader, who will hopefully take us through the slides.
So thank you, Matt, for the introduction to the operational aspects of NSTF. Before we move on to the technical capabilities, I would like to do an introduction. Sorry, my screen just stopped. I'm going to try and share it again. I'm going to give you an introduction to the general overview of the quality systems in place at RAL Space and how we have grown, how our systems have grown as part of the development of NSTF. At RAL Space, we understand how critical is our safety and quality in the integration and testing of space hardware. And we understand how important it is to have a quality system in place to support the success of the space missions. We have recognized this and have understood the importance of having quality systems in place that support and the effect that it can have on time, cost, and reliability of space hardware. We have adopted an integrated approach to quality assurance as part of the quality management systems in place at RAL Space. And we have built systems around key quality principles that enable us to fulfill the requirements from our customers and the quality standards that we have in place. Our processes, as Matt was mentioning earlier, are key and fundamental to the success of our testing activities. And we make sure that we have adequate processes defined to support our operations. We have defined roles, authorities, and responsibilities for our technical and support functions. We also make sure that there is sufficient resources and properly defined resources around our facilities. The infrastructure and the technical equipment is sufficiently defined to support the operations of our team. We make sure that we have suitable, qualified and experienced personnel in charge of the facilities. Basically, we're always making sure that we have the right people for the right jobs. And we work a lot with our stakeholders to maintain effective relationships, and the management of those relationships with our customers, our suppliers, are also fundamental in the implementation of quality systems. And we have a thorough, effective monitoring and auditing program that enable us to keep our systems in check and make sure that we make informed decisions. So throughout the development of our quality systems, we have made sure that we have suitable processes, people, and equipment to demonstrate that things have been done as intended to the desired level of quality for the space industry. Historically at RAL Space, we've had ISO 9001 implemented since 1999. So for over 22 years, we have maintained this level of quality in our facilities. To date, we still have this standard in place for the design and development of space hardware, as well as the provision of clean rooms for integration activities and testing facilities. In 2018, we decided to raise the bar with our quality systems in response to the needs of our customers. And from the process of consultations through the NSTF user group. And around that time in 2018, we started with the implementation of EN 9100, which defines more stringent requirements for the aviation, space, and defense industry. And after a couple of years of hard work and lots of paperwork, around December 2020, we achieved the certification against EN 9100. That was a significant milestone. The certification currently covers the clean rooms in our 100, the vibration facility, and the pirate shock testing facility. And we're intending to introduce the 5-meter TVAC chambers in our 100 through 2022. As part of the evolution of our quality system, we are also aiming to introduce the ESA standard for space test centers, as Matt mentioned earlier. And we're intending to have fully implemented this standard around end of this year or sometime next year. In September last year, we had the first pre-visit from the ESA auditing team to review, to make a preliminary assessment of the readiness of our facilities for this heavier standard. And the recommendation at the time was that we are able and should go for the full implementation of the standard. So at the moment, we're working with ESA to establish a timeline for certification. And our plan for the future is to have that standard implemented as part of the development and commissioning of NSTF. So hopefully be fully certified for the first test campaign from our customers. In terms of the quality and safety team, we have a core team supporting the systematic implementation of quality standards through the construction phases and later as part of the general operation of the facilities. Our team work and are fully integrated with the technical teams in promoting a culture of quality and safety in our facilities. We're fully embedded as part of the development of the test facilities. And we continue to work together with the technical and development teams throughout the implementation of NSTF. As part of the NSTF project, we have introduced quality and safety from the very early stages of the project, and the team have been involved through the design and development of all the facilities that included being participants and involved in the definition of requirement specifications, through the evaluation of suppliers and the selection of suitable suppliers, as well as managing any issues and changes as they arise. We have also been involved in critical design reviews, CDR, PDRs, through the site acceptance testing, and of course we will be also involved in installation activities and handover. By following quality principles and processes, we're ensuring that the NSTF facilities are designed and constructed to standards that are consistent with a world-class test center. As part of the later stages in the characterization and operations, we're also overseeing the implementation of quality and safety principles of the new test facilities for NSTF. We're currently working with the technical teams in the definition of test plans, and we will also be in charge, or will be involved in, performing independent reviews and inspections of the test facilities and the technical equipment as they become ready for handover, ready for operations. We will also participate in acceptance of functional performance and the approval of technical documentation in readiness for the certification process against the EN 9100 and ECSS standards. Before we move or we hand over the facilities into formal operations, we will be running the simulation of a complete test campaign using a representative test item that will go throughout all the facilities as any regular test campaign will do. That will give us the opportunity to define and test a number of scenarios, including the handling and movement of different test items across different facilities. This will help us to demonstrate the staff competencies and to fine-tune our operating procedures, providing assurance to our customers that we have tried and tested our equipment and our processes to the limit before we start with the first customer test campaign later on. I think this is the end of my presentation. I hope it gives you a broad idea of how we have quality, safety, and our customer needs at the center of our processes and in our facilities, and that you have some level of reassurance that your equipment will be in good hands when it comes to us, to the NSTF testing. Thank you for listening, and I will now hand over to the technical team for their own presentations around the capabilities of NSTF.
So thank you, Isabel. My name is Giles Case. I run the infrastructure group within the environmental test division, and I work for Matt Fletcher, who presented earlier. So the team as it stands at the moment, there's an image of us actually this morning. We've got about 50 years of experience in actually working within the space industry, and about 50 years experience in delivering the underpinning infrastructure needed to support building operations. That's primarily within STFC, but we do have some experience in other organisations as well. This is an image of the NSTF as you saw it earlier in Sean's presentation. You might be able to see the key parts of it. The entrance on the sort of facade to the right. You've got a personnel entrance here. But it's a little bit difficult to explore that using overhead drone imagery. So this is how it looks in CAD. And this is what I'll be using from this point forwards. So it looks simple enough. It's a few walls, a few doors. It's not a warehouse though. It's a little bit more complicated than that underneath. So to give you an idea, here's some of the mechanical and electrical services that sit just under the skin of the building. It's a very intensively serviced building. It's not like a regular building, and it's had its challenges both in design and construction, and will be quite demanding in the way it's maintained in the future. But if we cut that down a level and remove the plan, this is what we're going to talk about a little bit more. This is the actual layout of the facilities as they stand. So let's look at these a little bit more in detail. So we have an incoming airlock, as Sean mentioned. It's designed to accommodate a large vehicle, so we can actually take a low loader or an articulated vehicle and reverse into that area. We have extract systems that connect to vehicle exhausts, which reduce the level of contamination we may see. And we have a 26-ton overhead crane in there, which allows us to remove large containers from the vehicles. If we carry around anti-clockwise, we have clean room 1. So that's one of the clean rooms that's used as a base for a customer. It's got a separate change room, which isn't highlighted, but that's for when we're running at ISO class 6. When we're running at ISO class 8, it just ends up being a thoroughfare, a small sort of airlock to walk through. Next, moving around, we have an electromagnetics facility, and Matthew will talk a little bit about that later. That's another ISO class 8 area, so it's a fully clean facility. We then have the main hall, ISO class 8 again. This links all of the different facilities together, but it also acts as another, it serves another purpose. So if we have to do large solar array deployments, or perhaps we need to do some mass properties measurements, they can also be done in that main hall area. Moving around further, we have the dynamics facility. That's actually acoustically isolated from the rest of the building. There's a lot of design elements in there to try and stop the excessive sound levels, both from the vibration testing and from the acoustic testing, leaking out into other areas of the building or to disturb our neighbours. So that's it should be nice and quiet outside that particular facility. Moving around again, we have another clean room. So this is the second of the 2 clean rooms for our customers to use. It's, as per the others, ISO class 8, and it shares a crane with the next area, which is the TVAC preparation area, sometimes referred to as TVAC clean room. This is primarily where you set up equipment ready to go into the TVAC chamber, and Jen will cover some elements of that later. What you can see is actually at ground level, just below the highlighted area there, we have the EGSE space for the TVAC chamber. That's also temperature and humidity controlled and an ISO class 8 clean room. And so that's the basic of the areas. If I was to stand in the corner of the building and look towards the far end of the building and clean room 2, what would I actually see today? This is what I see. So you would have seen this image in earlier presentations. This is our sort of real-time now version of what is in the building. Bright, airy, easily accessible, everything on a flat level ground. So there's no thresholds or joints where things may get hooked up or we may have problems. It is worth noting that we have large access doors into all the facilities, and we'll cover those a little bit later. And the last thing to mention is the very, very obvious bright yellow cranes. So cranes is what I'll talk about next. So all of our cranes within the building, and there's actually 8 of them, 6 of them are shown. They've all been customized for use in the clean room. That's based on our own experiences of using cranes in clean rooms and the helpful advice from others in the industry. We actually consulted with various different providers of this similar services across Europe, and they all gave us some very, very useful advice, which we've taken on board. The way we've customized them is that we've actually got a lot of stainless steel components. The wheels, the rails are all stainless steel. And we've also got additional containment under motors, pulleys, and various other moving elements to reduce the risk of fallout and contamination. Typical crane hook heights are around 13 meters, which allows for a 8-meter payload on its end on a 2-meter tall stand and set of lifting equipment with a little bit of space to spare. And normally you would operate the cranes via a radio remote. So that allows multi-directional control in any one of 3 speeds. And the slowest speed is actually about 10 centimeters per minute. Having spent some time in the building, witnessing the movements of these cranes, 10 centimeters a minute is very slow. And it gives us the fine control we need for loading stuff on and off equipment. It's worth noting that these cranes can be operated manually as well, so without the use of radio control, for those people that may have security concerns about radio interference and other problems. All of these cranes can actually be used by our customers, as long as we see proof of appropriate training and we give the people a brief induction to the cranes themselves. So I talked earlier about the doors, and this is just highlights where the doors between the facilities are. They're all large format doors, typically 6 meters wide, although some of them are wider. They're all big enough to take full-size spacecraft on their end, on their MGSC. I should talk a little bit about supporting services. So all areas in the building have standard 13 amp UK sockets around, but we can provide adaptation if needed to suit other plug types. You'll note that the electromagnetics facility isn't shown with power because it's actually treated slightly differently to the rest of the building for the obvious reasons. All the power supplies in there are electrically filtered to stop mains-borne interference becoming a problem. We also have other standardized services within the clean rooms. These are provided by standard service panels. They allow common movement between all of the different areas with the same equipment, the same ability to connect to things in the same way. So these service panels are in 2 forms. The more highly populated one is actually shown in the image. This one includes the additional contamination monitoring and real-time displays. So the panels consist of an environmental monitoring system or sensors for temperature, humidity, pressure, and airborne cleanliness. High power electrical connections for distribution to the customer. These are also connected to our UPS system, which I shall talk about later. We have earth connections, both protective earth for safety and reference earth for other bonding potentials. And lastly, we have specialist gases distributed. The gaseous nitrogen on these panels is derived from our liquid nitrogen, so it's a very good high quality gas. Compressed air itself, which we supply, is dry, filtered, and capable of being delivered at quite high volumes. The idea for this is you can connect air skates to there and be able to move stuff around using the very flat and level floors with minimal effort. There's also an extract system, which can be used for removing inert gas or, for example, small amounts of debris that's released during a deployment or pyro event. It's not a vacuum system, it's just a gentle assistance extract system for removing that sort of thing. And finally, not highlighted, but can be seen in the image, is the traffic light beacons and the screen. They're actually part of the environmental monitoring system and allow you to understand when the room itself has gone out of specification. And these are where those panels are actually located in the building. You can see they're dotted throughout, and you have at least 2 or 3 panels accessible pretty much wherever you are in the building. So UPS and power. As many of you will know, the stable and uninterrupted provision of electricity is really very important for the safe operation of both our customers' equipment and the facilities themselves. As such, we have uninterruptible power supply system in the building, which is in turn recharged from a diesel generator. The UPS of power is available at each of the standard service modules, as well as other locations throughout the building, such as customer offices. The UPS power allocations are based on 2 concurrent clean room users, and each of those is allocated 50 kilowatts of purely UPS power. And because most of that electrical energy is typically turned into heat, that is matched by the air conditioning capacity of those rooms. It's also worth noting that in recognition that the amount of EGSE that a TVAC test will take and the compact nature of the EGSE room adjacent to the chamber, that also has 50 kilowatts of air conditioning capacity in there. It allows the equipment to stay in a nice stable temperature control condition. Well, I should also note, and didn't mean to say, is that the UPS and generator system also underpins the operation of the TVAC chamber and many of the other supporting services in the building. Uninterrupted operation of the TVAC chamber is very, very important because you're in a condition where it's quite a lengthy process to successfully recover from a failure event. So you need several days at times to be able to recover. And finally, our customers need a place to call their own. So both the first and second floor southern elevations of the building have dedicated customer spaces. So if you're renting a complete clean room, you effectively get part of one of the floors of the building for your own accommodation. So our customers are allocated an office space. In this case, it's been laid out for 29 desks, and the desks come as standard with the offering. You get a meeting room with a large display and video conferencing facilities. Plus, you get a local welfare facility, so including a small tea room, which has the ability to make tea, coffee, store food, and reheat food. There's also a small breakout space, which you can't see in this image, but allows for some independent time away from a desk or a meeting room to have your break. If you can see where my mouse is, it's worth pointing out here that these are actually windows in each of the areas. This allows you to overlook your clean room space and see what's going on with your teams. That's the same on both the first and second floors, but for programs that have some privacy issues, those windows do have blinds, and those blinds are closable from within the clean room spaces, so we can provide an element of privacy. And that's me covered for my presentation. Thank you for your time.
So my name is Ian Horsfall. I'm the head of the Dynamics group. So just to introduce the team first, we currently have 7 staff, including myself, in the Dynamics group. We're already running an AS9100 qualified group and have done that for a year by now. We have 2 more test engineers, or 1 more test engineer and a undergraduate intern arriving later in the year. So we'll end up with myself, 6 test engineers and an embedded numerical modeler plus an undergraduate intern in the group. In fact, the least experienced member of that will have 2 years of experience of operating a vibration facility. So we're already training in the key systems and practices of the NSTF and trying to get used to operating the bits of equipment and things we need there. The facility is a dedicated facility for vibration, acoustic and mass properties measurement, and I'll go into some detail of that now. So the dynamics hall is basically a 16-meter cube. It's acoustically and seismically isolated from the rest of the building. It's got 2 built-in 220 kilonewton shakers and they're installed in a way that gives us a high overturning moment resistance, which allows us to operate with big, heavy, tall satellites. They're optimized to work over the frequency range of 5 Hertz to 150 Hertz, but they have capabilities outside of that, up to around 2 kilohertz we would expect. But we'll know a bit more about the detail of that when we've finished commissioning. We have a data acquisition and control system linked to those. The data acquisition system is mobile and would normally be controlled from the control room. To give an idea of scale, we have a 5 meter square control room here, looking into the hall, although we have relatively limited view into the hall due to the thickness of the spaced walls, but we'll have CCTV to give us views in the areas we can't see easily. And we have direct data links, not only between the control room and the main floor, but also from that control room to other parts of the building. So if we're doing a release, a deployment, or a mass properties test elsewhere, we can control or at least back up data from the main control room by direct wire links without having to go through a network. So the vibration facility looks something like this, or the main facilities look like this. We have on the left our vertical facility. So this is again a 200 kilonewton shaker sat in a 200-ton top hat shaped seismic block, which isolates it from the building. It's flush to floor. The head expander on top of this is guided to allow us to operate these big, heavy, tall satellites. The table is 2.1 meters across and it's an octagon shape. And it has a stroke of around 76 millimeters. The horizontal facility can actually be operated in a number of different modes. So we can use it with slip tables, and we have a large slip table, which is 2.1 meters square, which in fact mimics the vertical guided head expander. But we can also run it with a 1 meter square slip table. And the reason we might want to do that is to reduce the mass to allow us to drive to higher G levels. And we can also disconnect that shaker from the slip table completely and rotate it vertically and use it in an unguided or possibly in a separate guided head expander system for smaller payloads, and again, where we want to run to higher G levels. And so the diagram down the right just shows you the sort of G levels we expect to achieve. So with the heaviest satellites on the guided head expander or large slip table, once we're up to around 7 tons, we'll typically be operating up to a maximum of about 2.5 G. And that's sufficient. The typical specifications at that level are only 1 or 1.5 Gs. As we come down in satellite size, we can use progressively higher G levels. And by the time, in fact, for an empty table, we can do 7.5 Gs with the guided head expander, so like 12 Gs with a large slip table, 22 with the small slip table, and something like 40 with the bare head. And those are not completely bare. Those assume that we'd already have some equipment attached to the top of that shaker, in particular what's called a force measurement device, or FMD. And then, so just to go into that and to also talk about interfaces, this is where we end up. The primary interface to all of the shakers is via a grid of M10 threaded inserts on an 80mm grid. The large slip table, that's 2.1 meters across, the guided head expander also 2.1 meters across, and the small slip table 1 meter across. However, we expect in more or less all cases to operate via a force measurement device. And the purpose behind this is it allows us to directly measure the forces on the interface and to notch or limit on those forces or on moments imposed on the satellite. And that's a standard requirement in large satellites. So what we expect to do is to attach a ring of load cells. And what you see in the 2 center diagrams there are this ring structure, the top one with 12 load cells in. Each of those load cells is 150 kilonewton capacity in the up-down axis and 75 plus minus 75 kilonewtons in the X and Y axis. We'd have a 12-cell array, an 8-cell array on the smaller types, and in fact, both the size of that and the number of cells is arbitrary. We're going to design a 12 and 8-cell of those, but we'll probably end up with some more in slightly different geometries. And on top of that, we'll put a test adapter. We will have a facility test adapter, which is shown there in orange on the right. Although it's worth saying, normally we would expect a customer to arrive with their own adapter, and the interface would be to the top of the force measurement device. But that facility adapter, at the top of that is a ring of 48 M16s on a 1260mm PCD. And that's as close as we come to a standard interface, in that pretty much all of the devices in the NSTF will have that interface somewhere on them. And that interface fits something like a standard Ariane 5 clamp band adapter. So it's a reasonably standard interface, but we will probably expect quite often that large campaigns will have bespoke interfaces anyway. The acoustic test, which is mentioned briefly, so the method we're going to use is what's called direct field acoustic noise, or direct field acoustic test system. And this is basically a large ring of Nebworth style speakers around the satellite. And on the right there is a photograph of a demonstration run for RAL Space about 3 years ago. I noticed a question in the chat saying it would be nice to play music through them. Unfortunately, one of the requirements of this is that you don't get standing waves in the center, and therefore the speakers are driven in an incoherent manner, and that is, they don't all move in and out at the same time. The result of that is, I believe that a kick drum sounds quite good, but music sounds rather strange through them. But these will be positioned in the vibration hall, and we can drive them typically from a control room, which is laid out in the main hall outside, with the main control of the data acquisition being done from the vibration control room. To support that, we're already using some software called MSC Actran to model the acoustic characteristics of the system in there. And on the left there, I just showed the sort of sound levels we'd expect to reproduce. That's actually a set of all the test specifications out of different launcher manuals. And what we need to be able to achieve is an overall sound pressure level of something of the order in excess of 140 decibels, with different levels, different parts of the spectrum. Mass properties, we're buying a novel type of machine from a company called Rasonic. This is called the Rasonic 6000F. And this is an oscillating machine. So what it does is it simply holds the satellite is put on that plinth, and the top picture shows the plinth by itself. And that plinth is suspended on a spherical air bearing in the center, and is very, very gently oscillated in each direction. And the force required to cause that oscillation can be read out and is used to determine the center of gravity, the moments of inertia, and the products of moments of inertia of the test item sat on top of it. The nice thing about this is that this is a mobile system. It's just a big hexagonal box. It needs to be bolted to the floor for safety reasons, but it can be used in different locations. We put the satellite on top of it, press a button, and about an hour later, it will tell us where the center of gravity is to an accuracy of a very few millimeters, even for a very large satellite. And allied to that, there's also a Faro laser tracker, which we'll use to index the satellite and the test machine's frame of reference. Just to finally mention instrumentation, our data acquisition system is a modular 512 system, for a 512 channel system from ProSig, which has 512 IEP and TEDS channels. Some of those channels will also operate strain gauges. It's a mobile system in 2 racks that can be moved around the facility, either with the satellite, either inside the vibration hall or in other parts of the facility. We have high-speed video. We have 3 high-speed video cameras, 2 very high-speed black and white cameras, which will run, for instance, at 10,000 frames per second at 1 megapixel level, but will go faster than that at lower resolutions. And we also have a full a high-speed HD TV camera that will give us 4K color video at 1200 frames per second. And again, so there's a trade-off of resolution versus speed on that. And we can use digital image correlation, which is effectively digital stereo vision, to give us full field displacement measurements of the fields that those cameras see. We have a large stock of accelerometers for loan. We expect to have several hundred and expect to land now maybe 150 or so at a time to a particular campaign, or more than that. Single and tractional types, and we have accelerometer calibration facilities as well. So we would simply rent on a sale or return basis the required number of accelerometers. And we also have a modeling capability. So we're using MSc Nastran, which is our primary mechanical modeling capability for dynamics, Actran, which is acoustics, and ANSYS Workbench, which we use for design work and other work within the facility. And that's a brief run through dynamics. Thank you very much.
So good afternoon, everyone. My name is Matthew Oldfield, and I'm leading the team that will perform electromagnetic compatibility and antenna measurements in the NSTF. And I'm pleased to have this opportunity to tell you a little about the team, the technical capabilities, and the processes that we're developing to carry out tests to ECSS standards. So first of all, the traditional photo, as it is now, of the team outside RAL Space building. So the electromagnetics team is a little different in that currently RAL Space does not have any EMC or antenna measurement services. So over the past 18 months, we've been recruiting a team for the NSTF. We now have the core team, which consists of 6 people. It includes a mix of experience levels from long-standing members of RAL Space to a fairly recent graduate. And we have staff experienced in operating near-field antenna measurement systems, in general RF testing, and those who have extensive experience in carrying out EMC tests to commercial and space standards. So now sort of an overview of the EMC facility itself. So that comprises a fully shielded anechoic chamber with 2 shielded rooms to either side, shown here in a cutaway view. So the large chamber in the middle basically has a 17 meters square tip-to-tip floor area. It's around 14 meters high. It houses a planar near-field vertical scanner against the north wall, which is that's the wall opposite the main entrance doors there. And as Sean and Giles mentioned, these are rather large doors. They're 7 meters wide. The clear opening is 7 meters wide and 10 meters high. The floor itself is a reinforced concrete slab with vibration damping for mechanical stability of the scanner. And this is sat on top of a copper sheet to complete the shielding for the chamber. As Charles mentioned, the whole facility is powered by isolated transformers on both the mains and the UPS supplies. And it's connected to the NSTF's Clean Earth, its reference earth. And this can be disconnected from the main building earth, the protective earth or dirty earth, if required. So on the left here, we have the control room, the shielded control room, from which we'll run the facility. And on the right is the customer's EGSE room, again shielded. There's around 78 square meters of floor area there. Both the control room and the EGSE room are normal height areas, single story. And there are a number of feed-through panels and feed-through tunnels and trenches from the EGSE room into the chamber for connecting the customer's EGSE to the satellite under test. So all the rooms have level floor access from the main corridor. And the main doors are actually a 3-leaf design. And there's a hydraulically operated drawbridge in this area here, which when it's down horizontal, it provides the level floor access, and when it's raised, it completes the shielding of the chamber in the door area. So here's a picture of a main chamber from taken during the build, and you can see the shielding. This is a picture taken from the main doorway, and you can get some idea of the scale there from the scissor lifting platforms, which are rather large multi-person scissor lifts on the left-hand side there, and you can see the 5-ton capacity crane in the ceiling. So a little more detail on the antenna measurement system. So this is designed for medium or high gain antennas up to around 5 meters in aperture diameter. It has a 12 meter by 12 meter XY main scan area, which covers most of the north wall of the chamber. It's a commercial system from NSI-MI. It has active Z correction to ensure that the required planarity is reached, and the goal for that is around 75 microns planarity RMS. We have sets of probes, including open-ended waveguides and dual polarization probes, and the transmit-receive hardware necessary to cover the frequency range there of 500 megahertz to 75 gigahertz. And it includes software to control the system, acquire and process the data, extract beam parameters, and produce plots of the antenna performance. Also included is a payload test suite, for determining important link budget parameters, such as the equivalent isotropic radiated power, the saturated flux density, and the gain over temperature parameters. And we'll be operating to the relevant ECSS quality standards. So talking of standards, during the site acceptance testing, the system will be characterized to determine the NIST 18-term error budget, so a sort of standard error budget for the system. And we have sort of operational goals for around 0.2 dB for accuracy of the peak gain measurement, and around 100th of a degree in the pointing. But this latter figure, that this is dominated by the accuracy, the knowledge of the alignment between the antenna and the scanner itself, and we have a laser tracker for best determining this. Again, during SAT, we have a loan agreement to use the ESA VAST. These are the standard verification antennas. There's a picture of the millimeter wave VAST there in the photograph. These are antennas which are used around the world to validate antenna measurement systems of all types. And we are also developing our own in-house versions at 2 frequencies, which we will use to regularly revalidate our system, and of course for training and diagnostic purposes if necessary. So the current status of the system, it's undergone its factory acceptance tests last year in the US. Due to space constraints, only half of the main X and Y axes were tested, but otherwise the tests included all the hardware. And I've just shown an example plot there showing the scan repeatability, just a simple cut that shows the repeatability, which is the squiggly line below the -50 level is good. So between now and handover of the system, we're planning we're planning a staff training program that will include online training from NSI-MI on the theory and operation of their scanner, the staff will be involved in site acceptance testing, and during that, or at the end of that, there'll be formal hands-on training with our system from the manufacturers. And subsequently, during their characterization period, we'll be working with the system and our in-house test antennas to refine our test procedures and to build and maintain the competency of the team. So the other aspect of the facility is the electromagnetic compatibility testing. So we are going to be provide testing compliant to the ECSS EMC standard, which is has the same numbering as the quality standard for facilities, but has an E for equipment, with the exception that we will not have any magnetic capabilities, no magnetic field capabilities, but we'll be doing the conducted susceptibility and emissions, the electric field radiated tests extended up to 40 gigahertz, and we'll have electrostatic discharge, ESD, and transient test capabilities. The facility will also support customers undertaking RF autocompatibility and passive intermodulation testing. So for that, we will have high-powered wall, which will be 4 1.2 meter square panels of absorber that can safely handle incident power of up to 3 watts per centimeter. And as an additional safety measure, we will have the ability to operate our hypoxic system, which reduces the oxygen content in the chamber to around 14%. This is to prevent possible ignition of the absorber if there's any hotspots. And that oxygen level is similar to being at an altitude of 10,000 feet, sorry, or just over 3,000 meters. So this could be used for sort of high altitude training. It's that sort of level, and it's considered safe for people to work in, for staff to work in, but there will have to be some screening for certain medical conditions. So the EMC equipment, we have a near complete set of EMC test equipment, including the power amplifiers for the radiated susceptibility tests up to 40 gigahertz, as shown in the picture of the rack there. And they are, we recently took delivery of those. So we're currently trialing the equipment as far as is possible without a test chamber. We're ensuring it works, that it turns on, and we're characterizing its performance, and developing the test procedures, and importantly, training the less experienced members of the team in its use. So after handover, we'll be able to fully characterize everything. For example, we'll be determining our background levels for the radiated emissions testing, and during this time, we'll finalize our test processes. I think we're making very good progress on the testing with the EMC equipment. For example, we recently performed some conducted susceptibility tests on some in-house hardware, which was found to be faulty during qualification tests at an external test house. So we were able to replicate the fault, provide diagnostic measurements, and after a hardware modification, provide assurance that the item would pass the retest. So the plot here shows the test levels that could be achieved by the test item before the modifications. This is the limit line, this is the desired level, which it's obviously not reaching, it's below the limit line, the red limit line. And then after modifications and retesting, you can see that the test level gets to the limit line, overlays the limit line, and the item subsequently passed the retesting at the outside test house. So this was a good exercise to confirm that we're able to test the required standards and to demonstrate the competence of the team in the setup so far. Okay, thank you. So that's just a brief overview of the capabilities of the EMC and antenna measurement facility. And if you have any questions, I'll be happy to try and answer them in the Q&A at the end of this session. Thanks.
I'm Cem Ömer. I'm the group leader of thermal vacuum tests, which is under the environmental test division. Today, first, I will provide you some background on our thermal test capabilities. Then I will focus on our large space test chamber, which is in NSTF. So in this picture, you're seeing 11 thermal vacuum test chambers, which are all located in Harwell campus and which are all in different sizes. They are located in 3 different buildings, so up to the STC2, including STC1, Space Test Chamber 1. They are located in R25 building, whereas STC2 and 3 are in R100 building. And of course, LSTC, Large Space Test Chamber, is in NSTF building. So what is simulated in these chambers? We are basically simulating the vacuum and the thermal conditions in space, which includes the deep space temperature and some heat fluxes that can happen. And as the facility operators, while we are simulating these, our customers are checking the capability of their space products, design performances, and the other performances. To simulate those, starting from the deep space temperature, the entire internal surface of our chambers are covered with black painted thermal shrouds, which are fed with liquid nitrogen or gaseous nitrogen. For the heat fluxes, we can be using mobile thermal plates, or we can use some calvots or infrared lamps. And most commonly, we are also using thin film heaters, which can be placed anywhere within the chamber. And for the vacuum side, we are using different types of vacuum pumps, including graphene pumps like screw, root, scroll pumps. And for the high vacuum phase, we are using thermomolecular pumps and cryogenic pumps. So as RAL Space, we have quite good experience in TVAC testing. I can say an average of 50 thermal vacuum test campaigns are completed each year, which involves university projects, some prime contracts and SMEs, and also they include some internal projects. So I would like to share with you some very important key projects that we involved and in which their thermal tests are conducted in our thermal test facilities. So Beagle 2 was tested in our facilities, which was an exobiology lander for Mars. Spire, which was a spectral and photometric imaging receiver, which was an instrument in Herschel Space Observatory. I think everyone heard about MIRI, which is mid-infrared instrument, which was an instrument, and James Webb Telescope. In 2016, we tested SLSTR, the sea and the land surface temperature radiometer, which was an instrument on Sentinel-3. And after a year, we tested SPICE, which was an extreme ultraviolet spectrometer, and which was designed for a solar orbiter. I think it was a mission of collaboration between the ESA and NASA. So to perform these tests, we do have dedicated thermal test operators, and we need to cover 24 hours of testing. So to do that, we do have 12-hour shifts. For the small chambers, we have 1 on-site staff and 1 on-call operator, whereas for LSTC, there will be 2 on-site operators in the control room. Currently, our number is 14, but the target is to have 20 at this steady state. And this slide, I would like to focus on NSTF. So this is a top view picture of the ground floor. The circled area is the dedicated area for TVAC activities. So here you can see the plant room where the pumps, the electrical boards, thermal conditioning units are placed. In front of that, there is a TVAC preparation room, which is the ISO 8 class clean room. And you can, so just next to it, there is again a dedicated space for the customers' electrical ground support equipments. So here is one of the recent pictures of the LSTC door. And there is another picture when it is opened, and you can see it's inside picture before the thermal shrouds installation. In this slide, you can see the first floor. And if I can start with the plant room, I can say there will be a mezzanine floor around the chamber, which allows us to go around, walk around the chamber during the preparation activities and also during the test. There is a door here which connects the mezzanine floor to our control room, where the operators will be placed. Next to that, the rest of the staff will be placed. And just left to it, there will be a dedicated customer meeting room. And left to that, there will be again a dedicated customer technical room where the real-time thermal test data will be provided to. So in this slide, you can see the key capabilities of our large space test chamber. So it will be in 7 meters in diameter and 12 meters in length. There will be 10 independently controlled thermal zones, which will be fed with different thermal conditioning units. So you can adjust the temperatures of these thermal zones independently. The temperature is adjustable between 95 Kelvin to 400 Kelvin, and the base pressure will be less than 1/10 to the -5 millibar. So it's going to have sufficient number of temperature data acquisition channels. It also involves RGA and TQCM capabilities. Again, you can see at the right side and at the front side, there is a good number of ISO-K type flanges and ports for the customer. And there will be also cooling water supply for the RF loads. As I indicated in my previous slide, there will be EGSC spaces, and you're going to have a dedicated loading trolley to load and unload the satellite into our chamber. So for the reliability and resilience of the LSTC, redundancy has been adopted where possible, of course. So for the vacuum subsystem, for example, you can see there are 2 identical pumping chains. One is on the left, the other is on the right. If you lose one of the chain, the other can take place and you can still maintain the base pressure. For the control system, for the critical devices, again, a redundancy has been adopted. For example, for the PLC CPUs, network switches, and for the servers, if you lose any of these, the other one can take place and the operation will continue seamlessly. And of course, in case of mains electricity cuts, there will be a dedicated UPS and generator which will take place. And lastly, I'd like to mention our loading trolley, which looks like this. So it's going to have 3 different interfaces, bolting interfaces. It's going to have motorized tilting function. So it's going to have also a motorized propulsion system, so you can pull and push your satellite. You can push it as backwards configuration, as it is seen here, and also as forwards configuration seen here. And when it is in the chamber, you can still have fine adjustment capability of pitch and roll axis. So in my last slide, I would like to show you how we're going to use the loading trolley. As you can see, the satellite is coming vertically by using an over crane, and it's attached like this. Then turn to the horizontal configuration. Then by using its propulsion unit, you can push it into the chamber. Then when it's in the chamber after finishing the last instrumentation, you can do fine adjustments. So this ends my presentation. Thank you for listening to me. So I will hand over now to Sir Nash.
Good afternoon, everybody. So I hope you've been enjoying the presentations from my various technical colleagues, and they are now all going to join me for some Q&A to run through some of the questions that you've been adding into our Q&A box. Thank you very much for those. So hopefully they're all going to join me on screen. So while that's happening, I'm just going to look at some of these questions. So one of the questions we had was asking about what interest have we received in the facilities from different groups. Now, I'm sure you can appreciate I can't go into any level of detail on that from a commercial sensitivity point of view, but needless to say, we've been really pleased with the level of interest we've been getting and the variety of it, given how early days we are with the facility itself and really getting under the skin of it. But it's all, yeah, we've got a lot of interest in the capabilities that we're able to put out there. But the first question I think that we need to address really is one for you, Matt, which was in terms of access to the facilities and prioritization for different missions. So there was a question from Chris in terms of UK, whether we're receiving any UK government subsidies and different priorities. Are you able to take on that?
Of course. So to answer the questions as they appeared, so there is no UK government subsidy for the use of facilities. We should always remember that UK government has built the facility, and that's a really important investment into the future of rail, into the future of space in the UK. In terms of our rates, we have created a set of rates for the facility, and we have benchmarked them and tested them against the available benchmarks we could make. And we are happy that they are commensurate with the rates that you might expect. And in terms of prioritization, all contracts are going to be dealt with as equal. They're all going to have their own terms and conditions, which we'd expect to be the same. And it would be on a commercial basis that we made the prioritization for the access. So once we've drawn a contract, we commit to dates, and then depending on changes, etc., that will be dealt with the contract. We're not expecting any governmental intervention to say this one takes priority over something else.
Thank you. Okay, so looking at some of the more technical questions that have come up, Giles, there was one here about crane setup. With the layout that you showed, it appears that access for the TVAC prep area is via clean room 2. Is that correct? Are you able to clarify that?
I can clarify. It can be accessed from clean room 2, yes, but equally it can be accessed from the main hall. So what wasn't obvious from the slides and would be more obvious from the photograph that I showed, it's actually behind Isabel. So from just behind Isabel's head to the chamber on the farthest left-hand side of the image, there is no wall. So it's completely free and open access between that main hall and the TVAC prep area.
Thank you. And another one for you, Giles, here. Are there facilities for spacecraft compatibility tests with remote control centres such as ESOC?
Yes, so I'm not an expert here, I will admit, but what I believe is required is effectively a high-speed data link between the facilities to allow some command and control testing between the payload or spacecraft and the launch center. That is something we've done ourselves before for our own programs. and it's also something we've done for some current tenants within this building who have a commercial relationship with us, where they've done some testing. We're lucky that being a government owned national lab, that we do have very good internet connectivity. So we do have two 100 gigabit lines that run out of STFC, and we are able to route and prioritize as we like on that data. So I don't consider it to be an issue.
Thank you. Okay, Matthew, one for you. Is there any possibility to do measurements with at least parts of electric propulsion components activated, but without thrust or extraction?
I would say that there is a possibility, but we would have to look very carefully at the risk assessments and associated with that. So yeah, I mean, that's something we can look into, but yeah, we'd need necessary risk assessments.
Fair enough. Okay, one for Ian. If acoustic and vibration tests are using the same space, how will this be scheduled?
The usual thing is to do acoustics after vibration, and you will probably do some empty chamber vibration tests on acoustics whilst vibration was taking place. We can't do that, so we would have to have a gap between a vibration test and an acoustic test. A slightly better way to do it is to actually do the acoustic test ahead of the vibration test, because that means we can effectively build the speaker arena, wheel the satellite into that arena and do the acoustic test, then move it across to the other test machine whilst the arena is dismantled. So it requires a little bit more time. We can't effectively run them in parallel the way a separate reverberant chamber would be, but we think we could do it with minimal delay compared to a completely free two separate facilities.
Okay, thank you. Jem, I think you probably covered this in your presentation, but can you just remind us what the number of independent thermal channels and associated temperature ranges for the large chamber?
So there will be 1000 T-type thermocouple channels and 96 channels for the RTDs.
Okay, thank you. So Giles, another one here for you. So we've talked a lot about the capabilities of the facility. Hopefully it's clear that it is open to users from outside of the UK, and we're happy to talk to people from anywhere to come and use the facility. What does that mean in terms of accommodation nearby for people who aren't local? Are we able to help with that?
Yeah, so I just saw that pop up. So we do have accommodation on campus here. We have a 130 room hotel, which is run by STFC. We also have access to a user office here on site that will help support people booking accommodation, providing local information, maybe access to people we've used previously for renting houses for short-term lets, that sort of thing, where you're doing a longer test campaign and you don't necessarily want to put people into a hotel. There are other alternatives we can help guide with.
Can I just add into that? So where the site that the NSTF is built on, we have the facilities of Diamond Light Source and ISIS, the neutron source and muon source, and the central laser facility, which have thousands of users every year coming to do that. So this is something that STFC and the organisation is well placed to help people to do.
Yes, and building on that, Matt, obviously we are a campus location, so there's a lot of different things going on around which also support that. Okay, another one for you, Jem. Do we plan to have a solar simulator in the thermal vacuum chamber?
Not in the NSTF, I believe, but it's a matter of investment. I think UK government and UK Space Agency should decide on that. Currently, we're just simulating the infrared simulation, not the solar simulation. So it does need an extra infrastructure, I can say. Currently, we're not thinking that, but in the future, why not? Yeah.
Like with all of these things, I guess it comes back to demand and who's going to use them.
Yeah.
Giles, I think this is one for you. Are there any export or confidentiality restrictions with use of the facility or test results?
As far as we're concerned ourselves, we don't, but a customer may have either security or confidentiality clauses or requirements. They'll be dealt with on a customer by customer basis, depend on their own needs. We are not an X-list facility at the current time.
Yeah, thank you. Okay, now we had a question a little bit earlier, which I think I'll need each of you to comment on. We've talked a lot about the facility and its size and its capabilities, but what would be the smallest system or smallest level of spacecraft that we might think to be testing for each of the different test stations where the capabilities we have in the NSTF are still relevant, but perhaps also we can talk about how that then links to our other capabilities on site. So if I start with you, Ian, because you're not muted.
Well, largely there's no lower limit. There are two things I'd say. Firstly, we have an existing vibration facility in the R100 building, the building behind you, in the picture behind you, Sarah. So the cutoff for that is probably about a 3/4 meter cube or 100 kilos. If you go down below that, you'd use the existing facilities in R100. Above that, you go to NSTF. There's nothing to stop you putting a small thing on the NSTF, but it will be probably more expensive to do that. The only facility which I think has a lower limit is probably the mass properties machine, where the fixed errors in mass properties measurement are of the order of 1 millimeter or so. So if you put a millimeter sized thing on it, the errors are equivalent to the size of your thing. But that's other than that, just a progressive loss with small things. So from our point of view, there isn't really a lower limit, and we just move to the other facilities for smaller things.
Okay, Jem, would you like to pick that one up?
Yeah, as I've shown, we do have 11 test chambers and for different sizes. I guess for the smaller satellites, payloads, and instruments, STC1, STC2, and STC3 can be used. Even the 1 meter chambers can be used. And for the satellites bigger than 5 meters in any size, so LSTC can be used. The advantage of LSTC is the temperature uniformity of the shrouds, because we're going to use GN2 thermal regulation, whereas we are using LN2 thermal regulation and its boiling mode with the current facilities. So if customers need a better temperature uniformity along the shrouds, they need to choose LSTC.
Thank you. And then Matthew.
Well, there's no lower size limit as such. However, I think it will be a commercial decision on the customer's part, in that we don't currently have a small payload or small instrument test rate. So yes, it would be a commercial decision, I think.
Okay, thank you. Okay, so a question here about from a recruitment point of view, which kind of encompasses all of you, but I'll start with Matt, really. Obviously, we've got wide plans to look at capturing talent from all different areas to support the team. Are there any things that you're able to do within that to think about promoting diversity as part of that requirement, or that demand for people?
So SDFC and UKRI spends quite a lot of time and energy thinking about its diversity policies. We have all sorts of policies. All of our recruitment advertisements, go through a diversity screening system to try and encourage the maximum amount of diversity that we get. There are various forums within our organisation for promoting and encouraging diversity. We have a fairly diverse workforce that we've hired so far from various different aspects you might look at. I'm not sure how else to answer that question.
Yeah, I think just to add up a little bit to that answer, Matt, as you were mentioning, there is a high emphasis in diversity across STFC and UKRI generally. And part of the recruitment also involves selecting panels that will provide the diversity within the panel itself and allow the candidates the interviews to provide a more diverse environment and more opportunities. So we're very fair and open institution, and that's also evident through the recruitment campaigns that we do.
Thank you, Isabel. Okay, I don't know if this is one for Matt or for Giles, but we've had a question here about foreign objects, foreign animals making their way into the building. So what steps have we got in place, or how are we going to manage the idea of the local wildlife sneaking its way in?
Nobody's rushing to that one.
So I did drop an answer into the questions as it was turning up. Airlocks are there to prevent that sort of activity from happening. Good housekeeping, and the fact that we don't have a huge wildlife contingent that's likely to run into the building, certainly not with 8 legs and 20 centimetres large.
There are some very famous images floating around of dogs running through clean rooms in various Russian sites, so it does happen, but we're not expecting that here.
Matt, a question here for you in terms of the characterisation phase and the current COVID situation. Is that all factored into the planning that you've put in place?
Yeah, so the planning is made assuming that we are not having something which is unusually disruptive. So should we have something where everybody has to run away from site for several months, I have no doubt that will affect the situation, but I do not foresee very unusual things occurring, but I'm not a COVID expert.
Great, thank you. And right, let's see. I'm afraid there's a question here about cost estimates. I'm afraid I can't do that live. That's just not quite possible for me to be able to come back to you with. Is there a possibility for a country outside of the European community can access the test facility? Absolutely, yes. We're very happy to talk to people from everywhere. What's the payload mass that the TVAC chamber guide rail can, sorry, I'm trying to read and think at the same time. Jem, the system that you showed in terms of the turnover rig for the TVAC chamber, what's the maximum payload mass that we can put onto that and rotate?
It's 6 tons.
Okay, 6 tons. Wonderful.
Just to add on that, so 6 tons would be a dry condition. So when we've said its payload is suitable to 7, that's because it's not dry. 7.
But the rails of the LSTC, Sarah, it can withstand up to 20 tons. So it's more than that.
Okay, but so the really
limiting factor will be the loading trolley. Yeah.
Yes. Okay, thank you. Well, thank you very much for bearing with me and answering all of those questions. I think we're just about running out of time now to be able to catch any more. So I'd just like to say thank you to everybody for joining us this afternoon for this session. I hope you found it informative. And obviously, thank you to all my colleagues for all of the information they've put together and presented for us. We are very much looking forward to opening the doors on this fantastic new facility, welcoming people inside it and being able to really see what it's capable of. If you're interested in updates about the facility, please do sign up to the newsletter that we have that gets sent out every couple of months. And of course, if you have any specific inquiries, please do get in touch with me. And last but not least, if you were joined at the beginning of the session and you saw the poll in terms of asking the question of how many baked beans can you fit inside the large space test chamber, well, I have it on good authority based on some very precise calculations that the answer was B. It's actually 438,711,980 baked beans. That may well include some amount of estimation for the source, but you know, room for maneuver in there. So thank you very much, everybody, for joining us. We will be running some further sessions to look in detail at some of the test facilities themselves. So I hope you will join us for those in due course.